Welcome back. This is the second point of section 1.3. We also need to know how to divide by square roots. If I write something like 4 over the square root of 6, you've probably seen this before. Math teachers don't seem to care for square roots in denominators. Myself, I don't mind them so much, except when they prevent us from seeing a simpler form of an equation. So let's say I had 4 over root 6, and I wanted to simplify that somehow. What if I had 4 over root 6 plus root 6? What if this was my expression I was starting with? Can this be simplified? Yes, now there's definitely an easier way to write this. I want to get this square root out of the denominator somehow, and here's how I'm going to do that. If I have 4 over root 6, I'm going to use a trick I used earlier in this lesson. I'm going to multiply the top and bottom by the same amount. In this case, it's going to be root 6 over root 6. See, I'm multiplying by the same thing divided by itself. You could cancel them back out and be where you started. This doesn't change the value. But up above, 4 times root 6, I'll just write 4 root 6. Down below, root 6 times root 6. Well, that's the number where if you multiply it by itself, you get 6. So when I multiply it by itself, I'm going to get 6. See? Now 4 root 6 over 6, I could simplify a little. I can cancel a 2 out of the numerator and denominator. Now be careful. I can't cancel a 2 out from under the square root and outside, so I can't call this 4 root 3 over 3. That's a different number. The 2 under the square root is only worth half as much. It's a square root of 2. But the 2 outside the square root is worth the full value. I can take a 2 out of the 4 and a 2 out of this 6, and they're worth the same since neither one's under a square root. Just be careful about that. So if I wrote, say, root 6 over root 2, that'd be the same as root 3, because I can cancel a 2 from under the square root in the top and bottom. This is not that case. So 4 root 6 over 6 is the same as 2 root 6 over 3. So I'm taking a 2, I'm multiplying a root 6 and dividing by a 3. Multiplication works the same whatever order you do it in. I'm going to call this a 2/3 of a root 6. So up here, I've got 2/3 of a root 6 and then a whole root 6. Well, a whole root 6 is the same as 3/3 of a root 6. So altogether, I have 5/3 of a root 6. And that's a lot simpler than 4 over root 6 plus root 6. So that's the form I'd prefer that in. So I don't so much care if 4 over root 6 is by itself, whether you write it that way or you write it as 2/3 of a root 6. But when it's with another term, it really helps to be able to turn 2 terms into 1 term. That's going to make multiplication a whole heck of a lot easier. So it's handy to have that skill. So if I had a number like 1 over root 2, by itself, we might as well leave it in that form. Other math teachers will tell you they hate it, but I don't care so much. But if I want to fix it up a little, I could multiply it by a root 2 over root 2 to make my colleagues happy and say that's root 2 divided by 2. So, turns out half of root 2 is the same as 1 divided by root 2. That's a fun property. So that's easy enough. But what if I had to simplify 5 divided by 1 plus the square root of 2? That's a nasty number right there. That's real gross. We're going to have to do something about this. Oh, weird. I just realized this is the first place this semester that we see my favorite factorization. What are we going to do with this? First off, you might be thinking, why don't we multiply the top and bottom by, oh, come on now, the top and bottom by root 2. If I do that, multiply by root 2 over root 2, it doesn't work. The top becomes 5 root 2, and the bottom becomes root 2 I have to distribute. Root 2 times 1 is root 2. Root 2 times root 2 is 2. I've made things worse. Okay, so what if I multiply by 1 plus root 2 over 1 plus root 2? What if I multiply by the denominator over itself? That's actually going to make things much worse. That's going to leave us with, on top, when the dust clears, we'll have 5 plus 5 root 2. And you can check my work here, but just trust me, the bottom's going to be a 3 plus 2 root 2. That's worse than what we started with. I don't like it at all, so we're not going to do that either. Neither of these has gotten us anything simpler, but there's something we can exploit. This is really cool. If I have a plus b times a minus b, this is called a difference of squares factorization, because what I get is I can distribute this. This is a times a minus b plus b times a minus b. So I distributed the a minus b to the a and to the b. Doink and a doink. Doink, doink. And now a, this is a times a minus a times b plus b times a minus b times b. So it's a squared minus ab plus ab, order doesn't matter, minus b squared. These two guys cancel out. That's what makes this so special, is when I multiply a sum and a difference of the same numbers, the middle terms cancel out instead of adding together, and you just get a squared minus b squared. So an application of this is if I want to do, hey, none of that now. None of that now. iPad's going wild. Where were we? Long lesson. Okay. Here we are. Application of this is if I want to do 1 plus root 2 times 1 minus root 2. In the end, this is my a, this is my b. 1 is a, root 2 is b. So I'm going to get 1 squared minus root 2 squared, which is 1 minus 2, which is negative 1. And that's a number without any radicals in it. So I'm going to multiply by this thing to get rid of all the radicals. I'm going to take 5 over 1 plus root 2 and multiply by 1 minus root 2 over 1 minus root 2. And that difference of squares factorization is going to get rid of all my radicals. This thing has a name. It's called the conjugate. So we call this multiplying by the conjugate. And that's the trick for getting rid of these two-term expressions in the denominator where one of them's a radical. You multiply by the conjugate. And now up top, I'm going to have 5 times 1 minus 5 times the square root of 2. I'm going to distribute the 5 to get my new numerator. It's going to be 5 minus 5 root 2. And down below, I said that my answer would be negative 1. Now, you can FOIL that out if you don't believe me, but trust me, it does follow this pattern. Dividing by negative 1 is actually the same as multiplying by negative 1. So this is the same as 5 root 2 minus 5. That's 5 times negative 1. 5 over negative 1 is negative 5. Negative 5 root 2 over negative 1 is positive 5 root 2. So this is my final answer. And this is a lot easier to work with than the expression we started with because we don't have a nasty complex denominator. Well, nasty two-term denominator, rather. We just have a nice two-term numerator and no denominator. Anytime I can get rid of fractions in a problem, I will. Fractions make everything more difficult, so if we can get rid of them, it's very handy. Let's see. I believe we already talked about higher power roots. So let's go ahead and do another example. Oh, here's a good one. Here's a real good one. I'm very fond of problems that collapse down to simpler things, and this is one of them. I know something about numbers that lets me set these problems up in a fun way. Let's take 13 divided by 4 minus root 3. What the difference of squares trick is telling me is I need to multiply by the conjugate. To simplify this guy, I'm going to multiply by 4 plus root 3 over 4 plus root 3. So I changed the sign on the root 3. Everything else is the same. So the numerator is, let's leave it alone for now. Let's leave the numerator. I don't want to FOIL that. I don't want to distribute that yet. I'm just going to say the numerator is 13 times 4 plus root 3. The denominator down here, the denominator is going to be 4 squared minus root 3 squared, right? That makes sense? If you insist, I can FOIL it up. It's going to be 4 minus root 3 times 4 plus root 3. You've seen this trick at some point for multiplying binomials. It's the faster way to do that distribution thing I've been doing. 4 times 4, that's first, the first 2. Then the outside 2, so that's this 4 and this root 3. Then the inside 2, that's this 4 and this minus root 3. So that's going to be a negative term. This is minus, minus 4 root 3. And then L for last. That's this minus root 3 times this plus root 3. So that's minus root 3 times root 3. This trick, FOIL for first, outside, inside, last, makes sure that when you distribute, you get all 4 of these terms here. So it's a shortcut for this distributing, is we're going to get all 4 of these terms eventually, so we can just do them in a list. And just like I said, these 2 terms cancel out, 4 root 3 and negative 4 root 3, and we're just left with a 4 squared here and a negative root 3 squared here. Well, negative root 3 squared, root 3 squared is 3, so 16 minus 3 is 13, and this is the cute bit that I set up at the beginning of the problem. The 13s cancel, and our final answer is just 4 plus root 3. Isn't that nice? So that is how you get a 2-term expression with rationals in it out of a denominator. Let's say we are all done with section 1.3. Join us next time for section 1.4, which is all about polynomials.